Good morning, everyone. My name is Bas Spargaran. No, I'm not in session 2. I'm in session 1. Would somebody be able to bring the session 1 slides up? Thank you. That's a good start. I'm hoping that I can control the slides a little bit. If you're able to allow me some control using the next button. I was told that was. Here we go. Very good. As I said, my name's Bas Spargaran. I'm the science theme lead, strategic science theme lead for the energy transition for the Geological Society. I started that earlier this year. And I'm going to be talking about giving you guys an introduction to opportunities for geoscientists in the energy transition, brackets, revolution. And I'm going to be taking you around this diagram in a relatively rapid fashion. I'm going to talk about opportunities in the energy transition, a little bit about fossil fuels, CO2, global warming, and then move into solar, wind, renewable electricity, carbon capture, spend a bit of time on storage, which is actually very important, geothermal, heat, and of course, the reason why you're here, the impact on future careers. So, as many, if not all of you will know, obviously we are experiencing global warming. It won't have gone unnoticed to you that in 2024, we actually had the warmest year on record. It was 1.55 degrees above pre-industrial levels. However, that was just 1 year. In terms of longer term averages, we are approaching 1.5 degrees above longer term pre-industrial levels. And of course, CO2 is being generated primarily by coal, oil, and natural gas being burnt. And you can see that the relative levels of CO2 emissions from non-renewable energy sources versus renewable energy sources are very significant. The global energy transition is actually changing very rapidly. Over the last 10 years, the investment landscape has changed to the point where now renewables are actually the largest investment for energy going forwards. And you can see that there's been an exponential rise in renewables. And in fact, when this slide was originally made, they were predicting that renewables would actually overtake coal in 2026. They have now overtaken coal in the first half of 2025. So it's accelerating. Europe and China are actually leading the energy transition. You may be surprised to hear. And in fact, in the first half of 2025, the use of coal in China actually dropped compared to previous years. So wind and solar have actually overtaken fossil fuels in Europe, which is very good news. However, it needs to continue and potentially accelerate. And despite recent backsliding, there actually has been an acceleration. You can see that actually down here in climate progress in the last 2 years. An example of that is what's happened in the Netherlands. Here you see a slide over the last 10 years of the variety of different energy sources that were used. The Netherlands had very significant use of coal and gas primarily. And you can see in green the pickup in both solar and wind. And then in the background, you can see the actual energy emissions, the CO2 emissions from the energy sources to the point now where it's actually a third of what it was 10 years ago. So we are actually in the middle of a transition and a revolution. And in the UK, you can also see what's happened to the CO2 emissions in the electricity supply side of things, not so much in surface transport or buildings or in industry. And in fact, this year, the UK's greenhouse emissions have basically halved since 1990, and the UK is actually on track with its path to net zero. As I said, we're in a revolution rather than just a transition. And that revolution is actually being dominated by what's happening technologically, and it's being led by China, no longer by the US or the UK in previous revolutions. Much of that is to do with solar and wind in the way that new ways to generate electricity is coming forwards, but there are also new ways to transport and store that electricity in battery storage and in the high voltage DC electricity lines. And then there are actually new ways to use that electricity in terms of electric vehicles and heat pumps. And it's also being dubbed the electrotech age by a company called Ember. And they have a very fascinating diagram here, a little bit too complex for us to talk to in detail, but you can see that solar farms, wind farms, heat pumps, data centers, and the digital age are all interrelated and based on a number of very significant technological cost initiatives that are working together. To the point now, really, where we can actually see that we are, in terms of offshore wind and solar, we're in the middle of the acceleration phase, and some countries, like Norway, have actually gone into stabilization phase for electric vehicles, where there's been a very high penetration rate of electric vehicles. So, why is this important? Well, because the cost has come down so massively. There's been an enormous drop in cost for solar, cost for wind, and cost for batteries since about in the last 30 to 40 years. There's been often a 99% drop in cost, and wind a little bit less so, but nevertheless very significant, again, driven by China. So I'd like to focus a little bit on solar and wind and batteries, and then we'll get on to some geoscience. Wind and solar are actually the fastest growing electricity sources in history. You can see the pickup of solar and wind. And again, when this slide was generated, it was about 6 months ago, but actually in April, solar took over from nuclear in terms of its electricity generation. And you can see examples of, even in France, where people talk about nuclear being actually just a stable baseload. In fact, in the summertime in France, it became a swing electricity generator because solar was cheaper than nuclear, and it actually overtook in the middle of the summer. Some countries, like in emerging markets, such as Pakistan, it's been so cheap and so easy to deploy solar that they've gone from 5% usage of solar to 25% usage of solar in 4 years. And the top 5 countries globally in terms of percentage use of solar are now Hungary, Greece, Netherlands, Spain, and Pakistan. There may be some surprises in that list, just because of what, the latitudes of some of those countries. But in the UK, wind has been the big increase. And you can see here, the UK is actually 5th in the world in terms of generation of wind energy, and 4th in the world in terms of its percentage share of energy on a global scale. So it's actually doing very well in the UK. But what's important is not just wind and solar, but also storage. And here you see in the US, the sale of batteries, energy, and the installation capacity of batteries picking up only in the last 4 or 5 years, to the point now where in California, they're able to store electricity during the day and then release it in the evening when there's actually a peak demand by using batteries. Now that works well on the short term on a daily basis, but batteries can't actually deliver that on a weekly or a monthly basis or on a seasonal basis. And that's where you guys come in. So just a couple more examples here. You can see the percentage increase, over 25% of batteries of demand is actually being generated by batteries in the evening peak period in June for California. And here you see in South Australia, 3 days in a row, the penetration of solar during the day, but also the amount of swing from 100% wind to 100% solar. And then here you start seeing the pickup in batteries mirroring what happened in California. So before I get on to some further geoscientific stuff, I want to talk a little bit about careers for you guys. I find this particular diagram very important. It's the Ikigai from Japan, and it's about trying to find an overlap between what you love, what you're good at, what you can be paid for, and what the world needs. And that helps to guide you in the choices of your careers and where you're at the moment. Careers can be very linear. They used to be a bit linear, more linear than they are these days. And you might think that you could go from university to an internship and then on to become an analyst or a manager and leadership position. But in fact, it's much more likely that it's a bit more messy. And in fact, to the point that you might be changing jobs a number of times during your career. And you might be a bit more entrepreneurial in that process. And you might want to volunteer for things like I'm doing now rather than being paid for it. But at the end of the day, it's about what you love that drives what you're good at. And then you need to find that overlap and see what does the world need in order to move forwards. So if I was graduating now, I think I'd be signing up for the MSc at Imperial College, which just started this October. It's a bit of a mouthful, called the Renewable Energy and AI and Data Science, Geology and Geophysics MSc, but it's got a nice little acronym called READY. Ready for the future. I'm a geophysicist by background. I like numbers and I like rocks. And that's probably what I would be doing, and that's what I love. But that's not for everybody. But it is important to look at what the world needs, and the UN 17 Sustainable Development Goals are a good guideline to follow as well. And number 7 is generating affordable and clean energy for the world. So how can you guys contribute to that? Long duration energy storage is actually what the world needs. It's got, and you can see, an acceleration of wind and solar and batteries, but there are actually 3 steps required in terms of being able to get to where we need to get to. First step, we're well on the way, and we're beginning to see storage and interconnection and flexibility in our grids. But we need more long duration storage and alternative fuels in order to be successful. So this diagram here is, I'll repeat this in the next slide as well, is about the amount of, or the amount of storage capacity, and this is on a log scale, going from megawatts to gigawatts to terawatt hours. And the vertical axis is duration in minutes, going from 1 to 10 to 100 to 1,000, or becoming a day, a month, 6 months. And you can see that batteries occupy this space, the short duration energy storage space. And battery energy storage is growing, but at the moment, you know, it started out 10 years ago, approximately at about an hour, and it's been going up. So, and now it's averaging around about 4 hours, but it's not long enough to cater for the swings in the demand in weekly or seasonal storage. Of course, you all know about hydropower, but particularly pumped storage hydropower can cater for some of the seasonal and weekly requirements. There are 2 examples of pumped storage hydropower in the UK, Electric Mountain in North Wales in Llanberis, and Cruachan, the Hollow Mountain in Scotland. Of course, they need mountains, they need lakes, and they need geologists in order to help them site and plan those places. But there's going to be another one coming soon, Erba in Scotland, and that's going to have about 40 gigawatt hours of storage. So it'll be about 4 times more than what we've currently got in the UK. But it's still not going to be enough. So we need to be looking at subsurface energy storage. The subsurface is where we come into our own as geoscientists. Salt caverns and storage in salt caverns are a proven technology that can be scaled. And you see the same diagram now in terms of storage capacity on the bottom, on the x-axis, and duration, just discharge duration on the y-axis. And this is generated by the USGS, color-coded now with whether it's geologically related storage or non-geological storage. And you can see all of the different areas that you guys can impact in terms of geoscientists and helping with those storage solutions. Many, many different forms of geoscience skills required, and there's transferability between the oil and gas sector, mining sector, and geothermal sectors. It's important to not just think about storage of electricity or its equivalent, but also storage of heat. And at the same time, hydrogen and CO2 needs to be stored in order to remove CO2 from the atmosphere or prevent it from getting there in the first place. So I'm sure many of you will have heard about green hydrogen, was generated by electrolysis of water. Blue hydrogen is still coming from gas, methane that's being burnt, but then it's got an additional component of CO2 carbon capture and storage built into it. Grey hydrogen has been the dominant form of hydrogen in industry in the past. Carbon capture takes many forms. The CO2 can be injected into the ground, but also there are a number of very active projects now, 2 in particular, one called HyNet Northwest and the other called the East Coast Cluster in the UK, that have reached final investment decision this year, and they are now moving forwards. They are committed to generate CO2 storage and hydrogen and power, and in particular the cement industries, which is hard to abate, have also started investing. So an example of that is up in the Northwest. This is the HyNet Northwest project, which is run by Eni, which is particularly focused around the CO2 storage and the CO2 pipeline that's being built. But it's being combined with hydrogen and a planned hydrogen network focused in that area, also connected to the current largest gas storage site in the UK, onshore. There's also a gas storage site offshore, but this is the largest one onshore, which will, I expect, be converted or expanded to also be able to store hydrogen. The next speaker, Frank Glass, will also talk about natural hydrogen, but I'm not going to talk about that now. I'll leave that to Frank. So I mentioned geothermal. Geothermal energy also needs geologists. We are not as lucky as some places around the world where they're able to provide conventional geothermal energy. The US, Indonesia, Philippines, Turkey, New Zealand, they're all part of the 1 gigawatt country club that is generating electricity from conventional geothermal. But in terms of impact on a global scale, many countries have actually done well to decarbonize the electricity component of energy consumption. But under the iceberg, you see that heat is still a very significant contributor to CO2 and global warming. And we are lucky enough in the UK to have had a coal industry that actually is now no longer producing CO2, but has left behind many disused mines that have the potential to generate heat as well. And some of you are in this room are actually already involved in that industry. So you can see that there are also, just like I showed you earlier about just subsurface energy storage, there are a variety of different geothermal systems that are underway in the UK that ranging from shallow to deep, some of them planning to generate power. For instance, down in Cornwall, where they have granites close to the surface, and they have double the heat flow of the average in the UK. The United Downs project is attempting to generate thermal energy. If they get that working, there could be also lithium coming out of the geothermal brines, and that will enable some lithium extraction. The companies like Tanrock Energy are actually looking at how to help distribute and have district heating for a number of places around the UK. I'm going to move on fairly quickly just towards the end now. Much of this is generated, the energy transition's really changed the diversity and the demand and the volatility and supply of a wide variety of metals that are being mined. You can see in this diagram just the explosion in the variety of different metals that are now required for renewable energy, and in particular focus just a little bit on lithium. This is again a log scale. You can see lithium was the sixth largest metal being produced globally. That is now forecast to almost increase by a factor of 10 by 2040. And there are a variety of different countries that produce lithium at scale, but Australia is the leading one, and Chile is next. They are, of course, still impacting the environment in a way that needs to be managed. You can see this is a satellite photo of the lithium evaporation mining that's going on in the Atacama Desert. one of the driest places in the world where they're having to use water to help extract it. But there are technological solutions to help with some of that. And I'm going to move on just in the interest of time. I'm going to finish off talking a little bit. Actually, I think I'll just skip the nuclear because I can see that there's a little sign coming about timing. So I'll move on to future jobs, which is why we're here. This slide, the diagram on the top left, highlights how salaries have evolved over the last 10 years or so, in particular in the green energy sector. And you can see that on average, in terms of all of the jobs in the energy side of things, they have been fairly stable, but green energy and clean energy sector has actually risen quite a lot in the last couple of years. So there's, in terms of that ikigai about can you be paid for what you love, you can. And there are also overlaps between the different components of the clean energy sector and the existing sectors. So carbon capture and storage, for instance, skills in carbon capture and storage are already there in the oil and gas sectors, but also are required in the hydrogen sector. And as I said towards the beginning, I'm a geoscientist, I'm a geophysicist by background. I love to see a little bit of seismic. Here you see an example of the 4D seismic that was shot over the Sleipner field. So that's CO2 that you're actually seeing in that section rather than hydrocarbons, but it's the same skill sets that are required. And in fact, it's forecast that over the next 5 years, there's going to be double the number of scientific technical roles required in the UK for the energy transition. So I'm going to finish. This is my last slide now. This is a bit of an advert for a webinar series that is commencing in December about the energy transition, which I'm organising. We're going to be talking about an introduction, and I look forward to. I'm going to talk about geothermal, wind, green and natural hydrogen, carbon capture storage, subsurface energy storage, critical minerals, nuclear, integrated energy, and finishing up with AI and machine learning and looking back. And that's all going to be taking place over the next year in the same time that COP30 in Belém in Brazil is happening this month. And in a year's time, I expect, it's not been guaranteed yet, but it looks like Australia will be hosting the COP31 in South Australia. In all likelihood, it'll be Adelaide, and it could be the very first COP that could be run with 100% renewables. So I'd encourage you all to join the energy revolution. Thank you. I'm going to hand over to Frank Glass, who's actually in Perth, Australia, and he's going to be talking through his experience and his advice for you guys about natural hydrogen exploration.
Can you see that?
Yes.
Yes, excellent. Okay. Well, good morning. My name is Frank Glass. I am the Chief Exploration Advisor of a small company based in Brisbane. It's called Gold Hydrogen. And I'm going to talk to you about natural hydrogen. Bas has already put it nicely in perspective that we need to work on the energy transition, need to feed that with all kind of options, of which hydrogen is one. The problem with hydrogen is if you want to use it as an energy source, you need to put the energy in first because you need to make it, and therefore it does no longer become an energy source, it becomes an energy carrier. Yeah, unless, of course, you can find it in the subsurface. And recently, we've been able to do that. And I'm here to tell you all about how that works and where we are in that process of finding hydrogen naturally in the subsurface, basically like oil and gas, but now hydrogen. And hydrogen is a really useful element, molecule, because of course you can burn it, you can extract energy from it without creating any carbon footprint, if you can take it from the subsurface and you don't have to make it upfront, right? So if we call natural hydrogen, something that is hydrogen occurring naturally in the subsurface. We also call it gold hydrogen or white hydrogen. Some people call it geogenic hydrogen or geologic hydrogen. It doesn't really make a difference. You need to make sure that you understand natural hydrogen isn't manufactured by humans. It is manufactured by Mother Earth. And therefore you need to do is extract it. And it's very useful. In the meantime, we've looked at different chemical reactions that could actually generate hydrogen in the subsurface, because of course we need to figure out how this works in order for us to predict where it sits and where we can find it. And there's currently 4 main theories of why hydrogen gets generated in the subsurface in geology, basically, right? So there's a serpentinization process where a redox reaction from mafic and ultramafic rock basically generates hydrogen. It is the iron-rich rocks. We call it, it's basically rusting, right? We extract the oxygen from the water molecule and the hydrogen gets released. You need water and you need ultramafic or mafic rocks, right? And they are in the subsurface in different geological domains. You can find these either shallow or deeper. Right? Then we have what we call the radiolysis. It's basically if you expose your water to high radioactive rock, uranium-rich rocks or thorium-rich rocks, then the radioactive energy splits the water molecule in oxygen and the hydrogen moves along the oxygen, gets bound by different other chemicals in the rocks. It's a bit of a slower process, but it still works. Then there is, we've got the over-maturation of organic source rock. It's basically when we have an organic source rock that generates oil and gas. If you cook that long enough and hot enough, eventually there is no more oil and gas released, and the remaining hydrocarbons break off and break out in hydrogen and carbon molecules. Not a very well-studied process, but something that could work. And then there is the Russian school, we call that. That is the idea that hydrogen is actually part of the core of the Earth. Yeah, it is galactic hydrogen. It sits in the core of the Earth and it's continuously moving out through the crust, from the mantle through the crust, for which you need big crustal disconformities and faults for you to see that coming through, right? So these are the 4 things, and whether you're in France or in Russia or in Australia or somewhere else in the world, there is always one that's the favorite. At this point in time, I'll point you to the bottom. Yeah, the Royal Society has issued a beautiful paper, that says natural hydrogen, in which you can, it is for free, you can download it, and you can read all about all the different processes that are in play for natural hydrogen and how it's been used. Yeah, it's a very useful document, and I urge everybody to have a look at it if you're more interested in natural hydrogen. Yeah, so here are a few hypothetical sections of where you could find the natural hydrogen kitchens and what would happen to it. Hydrogen is a very light molecule. It really moves really fast, and it's very reactive. It reacts to a lot of other chemical elements, and therefore retaining it is probably more the challenge than generating it. Yeah? So there's all kind of theories of where it would be retained and how it would be generated, as I said, but most of it requires either water or big faults and somewhere a trap to trap it. Now, this is very akin to what we do in the petroleum exploration world, where we look for movable resources and find ways where they can be trapped, and then analyze where you could drill them such that you can extract it. Yeah, so if you have any petroleum or hydrocarbon exploration experiences, it would be really useful if you want to look for natural hydrogen, because it does sort of similar things, but it's a much more useful element to have in the energy transition world. Yeah? Because, of course, hydrogen is, first of all, a source of energy if you can extract it from the subsurface and you don't have to make it. But it's also a really good resource in the chemical industry. It is useful for making ammonia, yeah, which is the fertilizer world where we need fertilizers in the world to feed us. But at the moment, the hydrogen used for making fertilizers is generated first by energy hungry processes. And if you can source it from the subsurface directly, then that would be a much easier way to generate ammonia. And on the other hand, we have methanol, green methanol or non-green methanol, depending on where you get your hydrogen from. Methanol is the future for the shipping industry. Yeah, Maersk and all the other shippers are working really hard to convert their big ships into methanol, running on methanol, because it is stable fuel and it can run those big ships over long distances, and they get out of the bulk fuel usage. So we can use that as well for that. So useful element to have if you can find it naturally. What happened in 2022? Zornig published a paper where he documented all the places in the world that he knew where natural hydrogen was encountered. And as you can see from the map, it's almost everywhere other than Alaska, South America, and Africa. Yeah. Now, doesn't mean it's not there. It just means that we haven't measured it. You know, these are holes where we didn't do any measurements. So basically, if we use Europe as a bit of an example, natural hydrogen is measured in a lot of places. It's not something that is unique. It is just not something that is being pursued with great vigor so far. Yeah. And you can see at the bottom, Australia has also done their own little research. We found many places where by accident natural hydrogen was found. The US has made an whole assessment of their potential, but most important is in a small place in Mali, they're actually producing it. By accident, somebody drilled a water well and tapped into a natural hydrogen accumulation. Yeah, it exploded, not very handy, but they managed to contain it, and they're producing this now for over 10 years and sticking it into a fuel cell where they're producing electricity for the local village. Now, so if you say, does it exist? Yes, it does. In Africa, it's already been done, right? On a small scale, but it tells you that the technology and the resources are there if you know where to find them. Yeah. This is a complicated problem. I'll tell you that. It's not easy, otherwise we would have done it already in multiple places. But it is technically possible and geologically possible, but we just need to be a little bit more sharper and more advanced in finding out exactly how it works. This is the Australian example. Yeah. In 1931, by accident, somebody drilled a petroleum well and didn't find any petroleum, but they measured hydrogen. Yeah? And then in 2021, a small company called Gold Hydrogen picked up the acreage next to the old well, and we drilled a well to prove that this was not a fluke. The hydrogen is actually there, and you can measure it with modern technology. Yeah? And here is what I call the hydrogen log of the Ramsay 2 hydrogen discovery. Now, finding hydrogen in the subsurface while you're drilling is not an easy task. It's not something that you could do with the same tools that you would find petroleum. We use what we call mud gas measurements for it. And in the column under Ramsay 2 mud gas measurements, there is a hydrogen column, and you can see the spikes in the hydrogen where we tap into little reservoirs that are filled with free-flowing hydrogen, right? And you can see already there is 1, 2, 3, 4 that we can identify straight away that are individual hydrogen accumulations at this one location. Right? So we can say already it is possible to find it. Right? Now all we need to do is find a way to extract it in commercial quantities. Right? You can also see up here the helium mud gas log, and you can see there is a whole spike under B where elevated helium is measured in the fluids in the reservoir. And that is a very useful combination. Hydrogen in the subsurface and helium have a sort of a co-occurrence. It happens a lot that you find them at the same place. Now, hydrogen is a really useful molecule for resources and energy, but helium is very valuable. Yeah, and especially when we start thinking about the nuclear energy transition, then helium is an essential element of that. Yeah, good. Not only in Australia have we done this, in the US, this is a company called Hytera. They have published their own logs. They drilled earlier this year, and you can see they also have a hydrogen log and a helium log, and you can see that they've got hydrogen spikes as well at different levels. So in other words, it's there. Yeah, it's difficult to find. It's more difficult to extract. Yeah, most places where we found it so far is next to old wells where by accident we found it previously or historically. Compiling all that information together and finding where we need to go to find the bigger accumulations is a technical geological challenge. Yeah? But we're not the only ones doing this. Yeah, the whole world is currently running mad in trying to find the technology and the geological domains that can actually demonstrate this to work. Right? In the US, the biggest company is called Coloma. It's got the backing of Bill Gates and Bezos and United Airlines and a few Japanese companies that have all put money in that company, and it's drilling 12 wells so far in the US, finding different locations for natural hydrogen. They're private. You won't hear anything what they've been doing other than rumors. Yeah. You've seen Hytera and there's a few others that are floating around in the US. Canada, most of the mining companies are now transitioning into natural hydrogen because and they have already got licenses and the subsurface knowledge, so they're transferring it over to the next resource. In Australia, there's a whole handful of small startups that have been trying to grab acreage and work the acreage to find the best places to drill, under which Snowfox, which is a UK company, has been participating in that. In Europe, the French are very strong on that, although there is a company in Spain that is working on a discovery of natural hydrogen. In Africa, there's happening. There are industry alliances that have started up where we start to talk between the different companies and try to find if we can together solve this problem. And there are investment companies that are desperately trying to put their risky money and supporting this industry as an upcoming industry. Right? It's an industry with a future. Yeah. Natural hydrogen is a very, very useful molecule, and we know it's in the subsurface and it can be extracted as a free resource, but we need help because the industry is too small and we need more brain power and passion to help this work. Right? There is a lot of resistance. Yeah, there's lots of old geologists that say, oh, natural hydrogen will never occur, or it's too small, or you'll never get it in commercial quantities. I would disagree with that. I think we can find it, and I think we just need to work a bit harder to understand exactly how it works. But so we need passion, yeah, to help us create a new lower carbon or a hydrogen-based society, and a natural hydrogen is a perfect input into that. Yeah. But we need geoscientists like you, but we also need chemists. Yeah, we need engineers, we need entrepreneurs, people that start up small companies, technology companies, exploration companies, development companies, specifically based on the natural hydrogen industry. We need some financial experts because we need to fund it all. We need influencers to help us spread the news and the knowledge. Yeah, and all of that has to come from the next generation and you as students. So come and help us find natural hydrogen and use natural hydrogen as part of the energy transition. Yeah. And that is all I'm going to say for today. If you've got any questions, feel free to raise your hand and ask them.
Fantastic. Thank you very, very much, Frank, for dialing in from Perth and giving us your time. We're going to leave the questions just in terms of timing. There's been, obviously, we've got 4 talks this morning in the energy transition slot. I'd like to introduce Gemma. If you do have questions, you can always feed them back to Frank if we can't find some of the answers from other people around the room. Gemma Bates, who's going to be talking about wind and submarine cables.
Hi everyone, it's good to be here today to talk to you about 2 of my big passions in my working career, geoscience and the energy transition. We're going to be focusing on offshore wind and submarine cables, so that's power cable interconnectors. So when we have renewable energy, not only do we need to be storing that energy, as Baz was talking about earlier, but sometimes we need to distribute that energy from power supply to demand. the green button. Oh, there we go. Lovely, thank you. So I'll just start by giving a brief sort of bio of my career. So I'm currently working for TGS 4C. They're based in Norwich, or I am based in one of their offices in Norwich, working as a marine geoscience consultant on power, cable, subsea interconnectors. But I started my career a few years ago now. I graduated from UEA, also in Norwich, with an environmental earth science degree, and BAS hired me, a Canadian oil and gas company, back in 2009. Had sort of 15 years working there, various different geoscience roles. Was based out of West London, but spent time in Canada, up in the Aberdeen offices and offshore on the rigs as well. And came full circle, moved back to Norwich to further my career in offshore renewables. So I started with a marine survey company, looking at sort of geoscience samples from the seabed, grab samples, then moved to Venterra Ordtech, which are looking for bombs on the seabed before you put the offshore wind farms down or the subsea cables. And so now at TGS 4C. Okay, so moving on. To me, geoscience has lots of different subdisciplines that sit within the overall umbrella of geoscience. So we've obviously got the more maths, physics dominated sectors in terms of seismic processing, acquisition, and the more interpretive elements, bringing all of the data sets together, pulling together geomodels, for example, and your GIS. There's a lot of sort of spatial data that is worked on as well within the geoscience community. And within all of that, everyone's working together, not just as geoscientists, but one of the great things is you get to work with lots of other disciplines. Working as a geoscientist with engineers is very rewarding, and that bringing that together in that multidisciplinary environment to provide a world commodity that we all need. Like, how many of us in this world aren't relying on energy every single day? Okay, so I'm just going to pull together now some synergies. So when I started my career 20 years ago, there weren't that many jobs in renewables for geoscientists. I think the first offshore wind farm in the UK was installed in 2003. And most part, they were looking for engineers. Maybe some geophysicists might have been lucky to get into renewables. A lot of work was in oil and gas. We've got, again, the 2D mapping, very big for exploration, consents, licensing, seismic acquisition, very, very evolved in the sector. We've seen some 4D seismic slides already. We'll see building that into interpretation, acquisition of rock samples, petrophysical data to get pulled together into subsurface models, very detailed, complex models down sort of a few thousand meters below the seabed so that we could drill these convoluted wells for our energy source. It's very similar to what we're doing as geoscientists, or at least not dissimilar, in offshore wind sector. There are a lot of geoscientists working on interactive mapping software. Web-based services are really key while data is being acquired, and also once the wind farms are installed, people are relying on this data on a daily basis. Seismic acquisition, for the most part, has been focusing on the seabed itself. So multi-beam, side-scan sonar, magnetometry, occasionally 2D lines, sub-bottom profilers, so they're looking at just tens of meters below the seabed. So in addition to the seismic data with the vibrocores and the borehole data, the ground models would be built. Again, it's just the only difference is scalability. We're looking a few tens of meters below the seabed here rather than a few thousand meters potentially. And another big change in the industry for renewables in the last 20 years, again, is scalability. So 20 years ago, we're looking at wind turbines that were about the size of the London Eye. Now, these wind turbines are almost as big as the Shard. And with that, the foundations have to increase. So these foundations require more detailed geological models to engineer these structures and make sure they obviously stay up. And with that, we need better data sets. So ultra high resolution 3D data sets, as per the oil and gas industry norm, is now becoming the norm in the renewable sector, which means we get to interpret this data and build geomodels from really great data sets rather than a few 2D lines and making it up, although we're at liberty to do that because that's a little bit of what we do. Okay, so in the offshore wind sector, here's on the right-hand side is just sort of a run through of the type of work that you would do from infancy of a project all the way through to installation, operations and maintenance, and decommissioning. You can see there's at least 2 large seismic survey elements that as a geoscientist you would be involved in as well. But you'd be involved in, for the most part, all of these to some degree. And again, just looking at scalability, we're not just working on a lengthy export cable route and an array at the end. When you look in detail at these arrays, there are hundreds of monopile bases, for example, here, and they're all connected with inter-array cables. These all need their own dedicated seabed surveys that need interpreting. And not dissimilar in the subsea cable interconnector world, we can see here on the right-hand side, there are a vast number of power cables across the world. We need a lot more. The more renewable energy we have, the more power cables we need to distribute that energy. If we've got a big storm going on in one country and we've got a surplus of energy, we can use battery storage or whatever kind of storage. If this goes on for a few days, we need to be able to move that energy to other countries that have a high demand, but they don't have any sunny weather or windy weather on those particular days. Okay, and then there's a little bit of detail on like what I would do on a day-to-day basis in my current role. So we're working with clients on data sets, mostly this sort of multi-beam, side scan, magnetometer data, where we're looking for geohazards, boulders, sort of ice field, glaciers, and also trying to find a lot of anthropogenic stuff that sits on the seabed. Currently, the project I'm working on, we've got vessels out at the moment that have found an old shipwreck, many boulders and fishing nets, washing machine, I think we found recently. No bombs on this one, but the last project I was working on, there were 28 bombs where the export cable route was. We can micro route around those as much as possible, but it's not always possible. So again, you might be involved in, probably not literally unless you've got some diving experience, but helping the divers go down and find these and detonate these bombs. The other teams we work with, the GIS team, very closely. So these glacial boulder fields, thousands upon thousands of boulders. You cannot just lay a cable on top of these boulders without some form of engineering or moving the boulders. So GIS and machine learning is really big for picking these boulders and helping us work through these challenges. Okay, so that's a little bit about sort of what you might do as a geoscientist in the offshore renewable sector. And here are just a few examples of some of the key players. It's not an exhaustive list, I don't want to get sued by anyone, but here are some of the operators in wind farms and the power cable sectors. In the middle, the geophysical surveyors, these guys all have their own seismic vessels, I believe. So you could go out and be a geophysicist acquiring the data on these, or working in-house with the processing and interpretation. And the supply chain consultancies, like myself, working more on the interpretation, supporting the operators. There's some UXO consultancies in there, as well as the more geoscience focused ones. Okay, and with that, I'll wrap up and wish you all success in your geoscience careers, and questions at lunch or over coffee. Thank you.
Thank you, Gemma. That was fascinating. That's really, really good. We've got one more speaker who's going to be dialing in from Abu Dhabi. Daniel Brook, who works for WeConnect Energy. You may know them as Subsurface Global, but they changed their brand last year. Daniel.
Hi, Bas. How are you doing?
Thank
you very much. Hello there. It's really good to be here and speaking to you today, even though I'm not actually in the room. But yeah, really grateful of the opportunity to come and talk to you about opportunities for geologists and geoscientists within the energy transition. So a little bit about myself. So I'm the managing director of WeConnect Energy. We were previously called Subsurface Global. We've been supplying people to the subsurface and drilling industries in the UK and the UAE for the last 17 years. As our clients diversified, went into more of an energy transition play, looking at low carbon renewables and hydrogen, our former name wasn't really suitable to for all the work that we were doing in the projects and construction and more of the engineering spaces. So we rebranded in 2023 to WeConnect Energy. About myself, I've been 15 years in energy recruitment, started out in London, had a 4-year stint in Australia, and I've spent the last 10 years in the Middle East, and 8 of that 10 years has been focused on energy transition and renewable energy. By way of an introduction, I wanted to give you a bit of an overview of the recruitment and the jobs landscape within renewable and conventional energy. So at present, renewable energy employment is at 34.8 million globally versus fossil fuel employment of 32.6 million. So that total of 67.5 million is forecast to grow up to 69.3 million by 2030. We expected during COVID that it was going to be the end of the oil and gas industry. Everyone was talking about how there's going to be no more oil and gas projects, there's no further exploration. And then when we had the war in Ukraine, that changed everything, and people realized that it's not a realistic idea that you can completely replace oil and gas with renewables. So that delayed slowdown in traditional energies has affected the speed of skill set migration from conventional to renewable energy. I think everybody thought back then that, well, you have one industry here slowing down and you have one industry here that's picking up. We'll just try and take people from here and we'll put them over here. Whereas this industry actually hasn't slowed down as much as people expected it to. So in renewable energy, we've had to look at other ways of bringing people in and solving these skills gaps. Most of the growth from that 67.5 million to 69.3 million is going to be driven by renewable energy jobs. Now, there is still going to be a growth in oil and gas jobs. So we're expecting 590, well, there were 590,000 new jobs added in oil and gas in 2023. However, fossil fuel employment includes coal, and coal is declining quite rapidly. So whilst oil and gas is going up, coal is going down, fossil fuels is staying the same, and we're seeing this growth of almost 2 million jobs globally coming from renewable energy. Worker sentiment. This is a really interesting point, because back 6, 7, 8 years ago, you would have never got an oil and gas person who wanted to shift and transition into renewable energy. COVID and that period of time did change that. But there's a lot of people now who are maybe sort of at the top end of their career that are thinking, I don't need to change. I can stay in oil and gas for another 10 years, and that's me. There's not really much of a need for me to transition. However, a lot of the industry now is a younger generation, and a lot of the people that have entered the industry in the last even sort of 15, 20 years, 86% of those people would consider changing jobs. And changing jobs is not just related to going to another company, trying to get more money somewhere else, or maybe looking for a promotion or an increase of skills or a different geography. That's also looking at where can I apply my skills in a different context. And applying skills in a different context is always a way to take a leap forwards in a career. Complexities in renewable energy projects are often less than upstream oil and gas. There's a reason why upstream oil and gas has always been very highly paid, and that's because some of the projects that people work on, some of the skill sets that are required, are extremely complicated. And we've seen as we've moved over towards renewables that sometimes the objection for an oil and gas person to go to a renewables project is it's just not that interesting. It's that there's not a great deal to it. A solar PV project, for example, is nowhere near as complicated as an offshore oil and gas project. However, opportunities do exist for highly paid, suitably complex roles to play a part in the energy transition. And what I'm going to talk to you about today is what some of those opportunities are. Now, I will put a little caveat on my presentation today. Each one of my slides could probably be a 1-hour presentation in itself, and I've got 10 minutes to go through about 10 slides. So I am going to do a real whistle-stop tour of this. There may not be time for questions afterwards, but you can always reach out to me on LinkedIn or any of the other socials or an email, and I'll be more than happy to answer any more in-depth questions that you might have. In terms of trends, what we're seeing and what we're looking for in allowing people sort of like yourselves to apply your skills in a different context is crossover. So we're looking at ways where we can apply the skills that you've amassed in universities or in your early careers and apply them into a different context within the renewable energy industry. So offshore engineering, for example, in offshore wind, has a lot of crossovers and similarities to upstream oil and gas projects when you're looking at offshore foundations, jackets, and offshore fabrication. Project management, as renewable energy projects get bigger, they get much more complicated. And you can't just have a single project director managing a scope of work. As they get bigger, you need to bring in a much larger management team and a management structure, and the skill set from the oil and gas industry is then able to be applied in a different context. HSE is another area here where, as the projects get more complicated, when you have more dynamics such as offshore, when you're looking at potential seismic activities as well, the traditional HSE skills that have been applied in renewables are no longer suitable, and it creates opportunities for people who've come from a technical oil and gas background to apply those skill sets then into renewable energy. Reskilling needs for hydrogen, carbon capture, and geothermal. So these big projects that are coming within the hydrogen and CCS and geothermal realms, there's nobody who works in those industries who's worked on something of this scale. So we have to go and find people who have similar experience, who can apply their experience in this context. So hydrogen, I was involved in a very large green hydrogen project in Saudi Arabia, which was the NEOM Green Hydrogen Project. And there was never anything that had been done of that scale before. So our client were looking for people who ticked all of these huge long list of options, and there were just no people in the world that did it. So what we had to do, we had to look at a balanced scorecard of saying, well, let's get a third of the people who've got Saudi Arabia experience, a third of the people who've got mega project experience, and a third of the people who've got hydrogen experience. And as long as you build a project in that way, where you've got enough people who bring all of that experience together, and you have a project manager and a management team who can get all of that work out of it, out of that team, we're then going to be in a position to actually succeed. younger talent drawn towards sustainability. So a lot of the people in the room are here because of energy transition, and we need to find opportunities for you to progress into this world. And as I said before, in 2020, many feared the end of oil and gas. In 2025, oil and gas is still growing, and there's no end in sight. So there's opportunities on both sides of the coin here. What I want to do is talk to you about what they look like. So the offshore wind market, as we've spoken about, so there's 1.5 million jobs globally in offshore wind. 60% or almost 60% of those jobs are in Asia Pacific. There's been rapid growth in Europe, US, and APAC. Renewable energy tends to be tied to population. So APAC is a huge market for offshore wind or for renewable energy in general because of the 4 billion population that's over there. Within that, there's geoscience opportunities. That can be geophysical surveys, geotechnical drilling, subsea seismic profiling, and marine biology. These are all skill sets that are going to be required in the offshore wind industry. And as we say, there's 60% of those opportunities, I would imagine, would be in APAC. Within carbon capture and storage, carbon capture utilization and storage, the jobs are poised to grow. It's currently a very small industry. It's got a very high growth potential because of its potential applications and supporting net zero. So what does that mean for you guys? Within geoscience, you can look at designing storage reservoirs, evaluation and monitoring of injected CO2, reservoir characterization, petrophysics, and seismic monitoring. I'm involved at the minute in a pioneering and almost a startup project in the UAE, which was a company called 4401. And a lot of the requirements that we're putting into there, which is a CC, is actually carbon capture storage project, not necessarily utilization. They're all subsurface positions. So we've got a subsurface manager in there, and we've got field ops for subsurface. So it's not a traditional subsurface job, but it's definitely something that there's a big requirement for. Hydrogen, both blue and green. We've talked a little bit about these two industries already this morning. Currently relatively small, 30,000 direct employees globally, mainly supporting steam methane reforming, which is blue hydrogen. It has a potential to reach 60,000 by 2030. It's very highly process-driven technology. It's complex, it's unproven. And as I mentioned before, mega project experience here is what's needed to prove to be scalable. Opportunities within geoscience here. So we've got underground hydrogen storage and developing geological hydrogen, which Frank touched on previously. Geothermal. So this is an interesting one. And when I was pulling this presentation together, I had to do a lot of primary research on this because there was not a lot of information out there, but it's a potentially huge market for geoscience, and one that we as a business will now be putting a bit more of a proactive business development focus on. It's got rapid growth potential six-fold increase by 2030, so an increase of around 1 million jobs. It's an easy transition from oil and gas. There's drilling and reservoir knowledge required. Degree enrollment declining. So all of the skill sets that are required for geothermal, there's a decline in the people that are applying to universities and going to university and learning those skills. So it creates a big bottleneck in the market and makes the people who have these skills way more valuable. And that can be things like resource exploration, reservoir modeling, drilling, logging, and monitoring. Critical minerals, we've talked about lithium, cobalt, rare earth metals to meet battery demand. Huge amount of growth in here, up 1 million jobs by 2030. Africa, 40,000 jobs and increasing. Geoscience opportunities, we're looking here for exploration geologists, geochemists, resource modelers, and the big challenge here, again, in these markets is addressing ESG issues. There's a lot of challenges about can you ethically source lithium for your car batteries, and the same with cobalt. So anyone who has experience with a background in geoscience, but also can put an ESG slant on it, will do well within the critical minerals market. And apologies for the typo on the slide that I've only just noticed. Role distribution. So what is the workforce going to look like moving forwards? Oil and gas is still going to account for 50 to 55% of global energy supply. Natural gas projects is projected to be the least declining hydrocarbon, so it will be the last one to switch off as the world moves forwards to renewables. In terms of the workforce, oil and gas roles are expected to make up 40 to 45% of total energy employment, and the share is steadily decreasing as renewables grow. By 2030, the balance is expected to tip further, but oil and gas, and particularly gas and LNG, are going to remain a vital bridge fuel and a large employment base. And gas in general, as I mentioned there, so gas projects are driving oil and gas growth in the Middle East and North America. LNG, huge opportunity market. Could talk to you for hours about how big it can be, and again, very highly complex, but not one for today. Gas will be a transition fuel as everybody moves towards renewables, and it can also facilitate blue hydrogen production. Opportunities that are there are going to be reservoir appraisal, subsurface, and gas storage. So recruitment challenges, what do I find difficult every single day? So skill gaps risks are delaying projects. We can't find enough people to put onto such projects, and that's in renewables and conventional energy. We've got competition for transferable talent across sectors. So people from engineering, they're going to be required in oil and gas, power, renewables, and low carbon, and it's the same from subsurface and drilling. Financial considerations from transitioning to renewable energy. So sometimes the salaries for renewables are not quite the same as what they would be in oil and gas, but that is changing, particularly now when we start to see some of the offshore wind projects that need the same fabrication people to be attracted to come and work on those projects from an oil and gas background. People are not just going to do it for the passion, you need to pay them the same, and that is now starting to change. And employer branding is key for younger professionals. So people want the company that they work for to have a good image and be doing good things for the planet. We've covered a lot of this stuff already. So the demand for geoscientists, it's going to be applicable across multiple sectors: geothermal, CCUS, offshore wind, hydrogen storage, critical minerals, and LNG. There's geographic considerations per sector. So where you want to go, for example, might alter the geography that you might want to go and work in. Offshore wind for APAC, for example, geothermal for New Zealand, and other areas like this. It's a scaling industry, and it's all set to grow as the demand expands. Last slide from me. There are opportunities within oil and gas due to retiring workforces. There are lower university admissions for geoscience courses, which means that your skills are going to be very valuable. And also we need to do our bit to attract people into the industry. Geoscience opportunities within the energy transition. So there are geoscience opportunities also within the energy transition. There's a limited supply of skills in there as well. Geographic considerations will drive your market opportunity. And the challenges here are project complexities, salary gaps, and opportunity matching. So making sure that all of that stuff comes together. Is it an interesting project? Is it where you want it to be? And is it the right salary and the right time? If you can get all of that stuff right, there will be plenty of opportunities out there within both the conventional and energy transition sectors. Thank you very much. I'll leave this up here for a second. If anyone wants to scan this, you can get in contact with me that way. And yeah, anyone can reach out to me on LinkedIn at any time. More than happy to embellish on anything that we've talked about here.
Thank you. Thank you very, very much, Dan, for your time and fascinating presentation again. Obviously, we're running a bit